Hello everyone, my name is Sina Pourang. I'm a PhD student in electrical engineering at Case Western Reserve University. I'm very happy to present my work at 2020 IEEE Sensor Conference. So my paper titled Monitoring Fibrin Polymerization Effects on Whole Blood Coagulation Using a Microfluidic Dielectric Sensor. In this talk, I'm gonna go over a brief introduction to traumatic hemorrhage and its consequence to blood coagulation disorders. And then I'll talk about the sensor design, fabrication steps, measurement setup, and sensor readout. Then I'll talk about the study design and measurement results obtained from those experiments. And finally, I'll give some concluding remarks at the end. Traumatic hemorrhage, which leads to coagulation defects known as trauma-induced coagulopathy, is a major cause of global mortality. Losing major clotting factors, platelets, and fibrinogen due to considerable blood loss are the coagulation defects in severe trauma. One of the critical factors of trauma-induced coagulopathy is fibrinogen depletion, which adversely affecting fibrin polymerization, which impacts hemostasis status. Early assessment of fibrin polymerization defects important for guiding appropriate therapeutic strategies in TIC mitigation. So to rescue hemostatic status, early, rapid, and comprehensive assessment of patients' overall hemostatic status at the point of care and point of injury is important to guide hemorrhage control, transfusion, and life-giving management of trauma. Next, we'll look at the rotational thromboelastometry. Rotem is the viscoelastic test of blood coagulation, which provides several aspects of clot formation process. In this test, blood placed in a cup and a pin placed into it. The pin starts rotating. When the blood coagulated, the viscosity of blood changes so that induces a deflection of a pin, which is measured optically and give us a readout like this. The readout has several different parameters which give us information about onset of clotting time, clotting strength, and clotting speed. Because the measurement technique has mechanical force in it, therefore it might interfere with natural coagulation process. Also, because of moving parts in the Rotem, it's not easily to miniaturize it, and to use the Rotem, it needs technically trained person. So currently, there is no portable point-of-care device to monitor blood coagulation dynamics outside of the traditional laboratory setting. Our technique is dielectric spectroscopy, which is the quantitative measurement of complex permittivity of any material over a wide frequency range. It's a fully electrical label-free technique, can give us information about the molecule characteristic of any material via interaction with electromagnetic waves. We previously shown that dielectric spectroscopy is sensitive to different aspects of clot formation like platelet function and coagulation factors. So we came up with this microfluidic sensor term as the ClotChip, which has the dielectric spectroscopy function integrated to microfluidic channel to form a low-cost, one-time use disposable cartridge that uses less than 10 microliter of whole blood, which is the volume of blood available using a finger prick, and give us a rapid assessment of patient hemostatic profile. And finally, because this technique is a completely electrical technique, so it can be interfaced with the CMOS IC for sensor excitation and response readout, and can be converted to a portable point-of-care platform. Now we'll look into the sensor architecture. The architecture of the sensor is a 3D parallel plate capacitive sensing architecture with the two sensing electrodes separated from a floating electrode via the microfluidic channel, which contain the sample under the test. This can be modeled as two parallel plate capacitors connecting in a series via a floating electrode. So we take a quick look at the ClotChip fabrication technique. So gold electrode is screen printed on the inner surface of the PMMA substrate, and these substrates were brought together by a piece of double-sided adhesive layer, which was laser micromachined like this to form microfluidic channel. The double-sided adhesive layer was 250 micrometer in height, which affect the height of microfluidic channel. There are contact openings provided so that the sensing electrodes can be interfaced with the impedance analyzer. Shown here is a picture of measurement setup and test procedure. We used an impedance analyzer to characterize and record measurements from a frequency of 10 kHz to 100 MHz, and the impedance analyzer recorded a measurement every 10 seconds for a duration of 30 minutes. A macropipette used to deliver human whole blood into the microfluidic channel, and the sample volume inside the microfluidic channel was 9 microliter. The entire experimental setup was recorded, and the experiment performed at 37 degrees Celsius. So what we tried to see is the temporal variation of real part of permittivity at 1 MHz, because permittivity at 1 MHz is sensitive to the formation and aggregation of red blood cells that's occurring during the clot formation, which can reveal different aspects of clot formation. These plots provide us with typical ClotChip readout figures. The temporal variation of permittivity at 1 MHz was recorded over time and is normalized to its maximum permittivity for the duration of experiment. We see that upon the start of the experiment, permittivity initially rises, then the permittivity is reached to a maximum at a specific time, and it refers to T peak, which indicates the onset of coagulation time. Then a second parameter was obtained from ClotChip readout, which is defined as delta epsilon R max, and it's defined as 1 minus the ratio of minimum permittivity after T peak to maximum permittivity. The parameter delta epsilon R max is indicative of clot strength and has been shown to change with platelet activity. In this study, we identify a third readout parameter in the ClotChip curve, namely Smax, which represent the maximum permittivity slope in absolute value after T peak is reached. Through a series of controlled experiments, we demonstrate that Smax can provide new information on fibrin polymerization effects on clot formation. Previously, studies have been performed with the ClotChip alongside Rotem. ClotChip's T peak parameter was correlated with Rotem's clotting time, or CT parameter. Rotem's CT is a clinically important indicator of a patient's coagulation status and is prolonged in patients with clotting factors deficiency or on anticoagulant therapy. A very high correlation between T peak and CT was obtained. Studies were also performed with the ClotChip alongside Rotem. ClotChip's delta epsilon R max parameter was correlated with Rotem's maximum clot firmness, or MCF parameter. Rotem's MCF is a clinically important indicator of a clot strength and is reduced in cases of diminished platelet activity. Also, a very high correlation between delta epsilon R max and MCF was observed in this case. In this study, we investigate the effect of fibrin polymerization inhibition on ClotChip permittivity slope readout. Measurements were performed by adding different amounts of GPRP, a potent fibrin polymerization inhibitor, to 300 microliter of citrate blood and mixing with 20 microliter of diluted tissue factor. To initiate tissue factor-induced blood coagulation, the samples were also recalcified by adding 25.6 microliter of 250 macromolar calcium chloride. The samples were incubated at 37 degrees Celsius for 15 minutes before adding the calcium chloride. The ClotChip sensors were filled with 9 microliter of the mixture and kept in a thermostatic chamber at 37 degrees Celsius during the experiment. In this study, we compared the ClotChip Smax to Rotem alpha angle. The Rotem alpha angle parameter is a measure of fibrin polymerization and kinetic of the blood clot, and is known to be affected by different fibrin polymerization levels. These figures shows the ClotChip readout parameter, Smax, and Rotem alpha angle for 4 different GPRP concentration of 0, 0.4, 0.5, and 0.65 milligram per milliliter. As can be seen, the ClotChip Smax and the Rotem alpha angle readout parameters both decrease for higher concentration of GPRP, corresponding to higher level of fibrin inhibition. We also assess the correlative power between these two parameters. As shown in this figure, the ClotChip Smax exhibit a strong positive Pearson correlation of 0.883 and p less than 0.001 for 12 tests. This shows that the ClotChip has the same level of functionality as Rotem, which is the clinically important assay for monitoring fibrin polymerization effects on whole blood coagulation. However, the ClotChip can be considered as a point-of-care device and can be used in the location where the Rotem cannot. Finally, SEM imaging was performed to ascertain the GPRP effects on fibrin polymerization during the clot formation process. These SEM images of blood clots for untreated and GPRP treated with whole blood samples with final concentration of 0.6 milligram per milliliter that were tested with the ClotChip. As expected, the SEM images revealed a much lower density of fibrin strands in the GPRP treated sample due to fibrin polymerization inhibition. To sum up this presentation, we saw that microfluidic dielectric sensor was developed that was capable of rapid assessment of fibrin polymerization effects on whole blood coagulation. In particular, a new parameter Smax were obtained from ClotChip readout provides such information. We have observed a strong positive correlation between ClotChip Smax and Rotem alpha angle. And finally, our future work will focus on fibrinogen deficiency and hyperfibrinolysis, two critical aspects of trauma-induced coagulopathy. Thank you.